now that we know that it is only the transfer of electrons that is responsible for positive and negative charges, we come to an interesting application of this that is called charging by induction. Okay? Charging can be due to number one, it could be due to friction that we have seen, no? Silk cloth rubbed on the glass rod, charged. Glass rod got charged. The second one is conduction. There is also something called induction. What is conduction? You touch a positively charged rod onto a conductor. The conductor itself gets positively charged. We will come to that after the induction also, right? More into that. If you touch a negatively charged rod to a conductor, the conductor becomes negative. That is charging by conduction. Then there is charging by, rather I should say charging by induction here and charging by conduction. This we'll see later. Friction we have seen, so we come to induction. Now what happens if I have a metal sphere that is mounted over an insulated stand? Okay, this is an insulated stand. This sphere is made up of metal. Close to it, I bring a rod which is positively charged. It could be the same glass rod that had been rubbed with silk cloth, right? Now let us understand what happens. This being positively charged and the unlike charges getting attracted, we had seen unlikes get attracted, the electrons, this metal is characterized by a large number of free electrons. Metals are characterized by a large number of free electrons. A large number of free electrons. Free electrons. Okay? Characterized by a large number of free electrons. Okay? What happens? They are electropositive in nature. Say sodium. What happens? It has got one electron in the valence shell. So it has a tendency to donate that electron. Okay? After the, okay? So that means that electron is held very, very loosely with the sodium atom. So what happens? Even slightest of energy and the ambient energy at room temperature is enough to kick off those electrons so that they no longer belong to the parent atom. Okay? And this happens with so many of the electrons. And we understand only 23 grams of sodium will have any number of sodium atoms, right? And that will give you any number of electrons. Avogadro number of electrons, and that is nothing like we know, like right 6.02 into 10 to the power 23. Okay, so billions of billions. Okay, and more than that, billion is 10 to the power 9. So what happens? Those electrons, they keep on moving around in the bulk of the matter. And at one time or the other, okay, they keep on moving about the atoms, right? So they move like a cloud from here to there in a random motion. More of it we'll see when we are doing electricity. So what happens? It is known as an electron cloud. So metals are characterized by a huge number of free electrons. while insulators don't have a large number of free electrons. It's not that they simply don't have any single electron. They too have some electrons, but they are very, very small. Okay, very, very small. The number is so small that there will not be any perceptible current even if you apply large voltages across it. Okay, so fine. So this has a lot of free electrons which are not held by their parents. So what happens? There is a conglomeration of, there is an aggregation of, accumulation of some electrons out here. Why? Just because this positive charge attracts the negatively charged electrons. That's all. That's why. Understand? Did we get that? Fine. Now what happens? Now what happens? What happens? These electrons have migrated. So now they are bound. Correct? Now they are not so free to move. So some of the electrons, they got bound. That means some of the atoms remained uncovered. Do you understand that? Currently what was happening, these electrons were moving across the atoms, and though say this atom lost its child electron, the electron which belonged to it, but at some point of time it'll see some other electron fleeting across it, moving across it. That's how it will remain neutral. But now what has happened? Some, by some we do not mean 6, okay, millions, billions of electrons, they suddenly get stuck at a point. Now those billion electrons will not be able to pass through the atoms. So some atoms will have uncovered charges. So they'll become positively charged. So let us say the immediate neighborhood becomes positive, the atoms, and the atoms, they are not moving. Let us try to understand. They are not moving. They are stuck. So say some of these electrons are there. So these atoms which got stuck here, they suddenly tend to become a bit positively charged. So what happens? They take electrons from here, from the cloud itself, okay, and that cloud makes sure that they remain neutral, but then these become uncovered. In the net, and they'll pull. So ultimately what happens? The atoms here which are not able to pull the electrons just because they are at the end of the land. That means the conductor ends there. They do not have anything to their right from where they can pull the electrons. So the impact of this positive charge is that near the positive charges you have got negatively charged electrons, while farther away from it you have a positive charge. Now when we were being taught this subject, we were told that due to this positive, the negative charges get attracted and the positive charges get repelled, and they come to the end. Now that is a flawed logic. Okay, why is it flawed? Because positively charged, when you say positively charged, it is protons, and when you say protons, it means you are pushing the nucleus because they reside in nucleus. It means you are somehow saying that the metal that was here has flown to this place. Does not happen. Does not happen. Okay, and it was a huge confusion for me. How positive charge? From where did you get the positive charge? And it is again a flawed logic to tell that it is protons which are positively charged. Because yes, they are positively charged, but they will not flow. This is not a liquid metal. Okay, that does not happen. So it is the impact that travels, right? The impact travels. Okay, the uncovering of the uncovered charges, they travel. Fine. So that's why I said they first tend to become uncovered, then they pull the electrons, and it is that impact that travels, and the atoms here, they in the net become deficient in electrons. And it is not that no electron goes and passes through them. You will soon see, because they are randomized motions. But in the net you can say that on an average there will be a positive charge here. We get the point?
So, but the uniformity of the metal remains the same.
It remains the same. Okay,
So why don't the uncovered atoms, which are positively charged, attract the electrons back from where they were? The
I didn't get it.
atoms that are uncovered there,
Hmm.
which are positively charged.
Yeah, here.
Yes.
Yeah.
Why don't they pull those electrons back?
No, because these are held with a greater force. Due to proximity of that charged rod, you'll soon see when we go to Coulomb's law, that those charges, the force of attraction is more. That is the whole trouble. You know why those which are covering these, the second line.
So why don't we make positive signs over there? Why did we make it just on the periphery of this thing?
No, what happens? See, this attracts. So this will not have power to pull this back, but this has power to pull the electrons here. Why? Because the force on this due to this is lesser, so it pulls. First of all, it becomes positively charged. Next, the pull on these electrons is more for this than that. Pull for the electrons here is more than this. The pull due to this on the electrons keeps on decreasing as you go away.
So when we say that there are electrons there, so that means electrons from all the atoms in that solid body have come at the come near to the rod. All of them.
Oh, no, not all. Not all. This does not have power to pull those electrons. You'll soon see. Actually, the moment this kind of thing happens, there is an electric field from here to there. That electric field actually has the tendency to pull back those electrons. Okay.
So as soon as we remove the rod, it will come back to its original.
If you remove the rod, it comes back to its original position. If you remove the rod, yes, it comes back to its original position. It has only got redistributed. See, the electrons have not gone anywhere. We have not even touched this rod, right? We are just keeping it away. So it is just that there has been a lopsided movement of the one-sided movement of the electrons to one part of the conductor. Understand? Now, once you understand this, what happens, and this we do in the beginning only, but just to make you understand, so in fact we keep a another metal sphere touching this. So this impact actually travels through this to this point. You understand? The thing that I showed you for this, that actually travels, and this positive charge, instead of accumulating here, will get accumulated here. Understand? Do we see that? We see that? So in the beginning, that was to make you understand. Okay, in the beginning only we keep these two metal spheres touching each other, so that this becomes highly negatively charged while this becomes positively charged. Now, so in effect what has happened, the electrons from this metal sphere has traveled to the left one. An excess of electron has traveled to the left, and this is left deficient. Now what happens? Let us try to separate them out. Okay, let us try to separate them out. So I remove that proximity. They were touching earlier. I separate them. I separate them out, keeping the rod here only intact. And this remains. And now you remove the rod. So what happens? This negative charge gets uniformly distributed, and this becomes positively charged. So you see what has happened? Do we get what has happened? We have not done anything. We have not touched. We have not had any friction. We have not had any friction. And we have been able to charge both these metal spheres, oppositely charged, just by holding a charged rod near to the two metal spheres. Right? Now, do we always need two spheres? The answer is no. You can do it also by one sphere. Okay? For that, let us try to understand something called earthing and diffusion. Okay? See, if I have a positively charged rod, okay, and it touches a metal wire, say like that, what happens? What do we expect to happen? What do we expect to happen? We expect this metal conductor, the rod, to get positively charged. Why? Why? Because because this rod is positively charged because of deficiency in electrons. So this has less than it should have, and this has what it should have.
Normally.
Okay? Now what happens the moment you touch it to this? So what happens? Since it has what it should have, some electrons from here move to that rod. Okay, so this becomes less positively charged, while this also develops a charge. If you touch it in the second go, if you
After some time, the rod will become neutral.
no, if you touch it, then this will become a bit less negatively charged, while this will become negatively charged. They cannot become neutral, because if they become neutral, it means they have some excess electrons from somewhere.
See, only the rod.
This, no. You understand? If it becomes neutral, then it has what it should have, so it starts taking back the electrons. So that won't happen. You understand?
So the total.
It will never so happen. So there will be an equilibrium kind of thing due to the electric field that is established inside, and it will settle down at a point.
Both will have the same charge.
Both will have the same charge? No.
Why?
Deficiency.
No, deficiency, yes. Like, there were 3 electrons missing in that.
You don't go into that, because that requires the potential to become equal. For the charges not to be flowing from one to another, it requires the potential to be equal, that has a